My name is Robert Freitas. I am the Senior Research Fellow at the Institute for Molecular Manufacturing. I am a nanorobot theoretician.
Eric Drexler talked about nanosystems 20 years ago and laid out a vision of what nanotechnology ultimately could be. What progress have we made in the last 20 years in verifying and confirming the basic foundations of that theory, and also in terms of actual practical parts of that vision having been put into practice?
I think in the last 20 years, Drexler's theories have been confirmed to the extent that we have been able to test them. So far, nothing that he wrote in Nanosystems has been shown to be wrong of any substance. On the theoretical side, we have progressed to nanorobot designs. We have many nanorobot designs. We have many machinery designs. We have designs of devices which have, I think the last one was 25,000 atoms. It's a very large, complicated gear structure. In the 90s, there were many designs for bearings and gears and small manipulating devices and various parts that had several thousand atoms. So we're starting to get a good library of nanoparts built up. We haven't gotten anywhere near the point where we're doing the system integration on them yet. But slowly but surely, we're putting the pieces together of doing the design work. There have been a number of experiments where atomic force microscopes have been used to do pick-and-place operations on individual atoms, particularly hydrogen atoms and carbon monoxide molecules, which is just a carbon and an oxygen atom. And there has been one notable experiment done in 2003. It was the first time mechanosynthesis has ever been done in the laboratory, which is purely mechanical chemistry done at a tool tip. And it was a silicon atom. And they pushed a silicon atom down on a surface and it stuck, and they pushed down again with a different force and it came off. And so we know that we have a proof of principle that mechanosynthesis should work. Now we just have to finish designing the tool tips and then build them experimentally and test them.
Is there some idea of a roadmap from where we are today to actually making these nanofactories feasible?
Well, my colleague Ralph Merkel and I have started something called the Nanofactory Collaboration, and we have approximately 24 researchers who are participating in it. And we're starting with diamond mechanosynthesis, but the long-term goal is to work toward all the components you would need to be able to build a working desktop nanofactory. We've estimated that if we had proper funding and proper focus on the objective, the time would take approximately 16 years for the entire development operation. I think the 2020s will be the decade of the desktop nanofactory, and the 2030s will be the decade of the nanorobots. We might see a few nanorobots coming in at the end of the 2020s, but I think the 2030s will be when they are deployed medically in a large way and start to displace most other forms of medical technology. Well, I guess the ultimate start of nanotechnology was roughly 1906 when they first proved that atoms existed. It's hard to believe that only 1 century ago there was debate about whether atoms existed. There was no experimental proof yet that they definitely existed. So we've only known that for a century. After that, I suppose Feynman's room at the bottom talk, where he laid out for the first time the possibilities of building very, very small machines, but it wasn't a serious scientific discourse. It was a dinner talk, and it was sort of left to Eric Drexler to put everything on a more technical basis and put some numbers to it and establish that this stuff was actually feasible, that you could build structures atom by atom and make machinery at that scale, and that it would work. In the 1980s, I did a study with NASA on self-replicating factories on the moon, and we worked out a design for that. And we had looked at how to do it with microscale technology, with things that were microns in size, but we never thought about going all the way to atoms. And I read one of Eric's books. Actually, it was his most popular book, Unbounding the Future. And I looked at it and I said, wow, this is great stuff, but he's being so conservative in this book. Well, I found out that was because he wasn't conservative in his other two books, in particular Engines of Creation, where he laid out a lot of detail about the applications, and Nanosystems, which is just a fantastic technical book, which laid out all the technical details. And once I saw that, I realized that the best and highest application of nanotechnology would be the medical applications. I immediately contacted the Foresight Institute and I said, is Eric writing a book on the medical applications? And they said, no, he's doing other things right now. I said, well, I guess I'll write that book. So that was sort of how I got into it, writing a 3-volume set, which has now become, it's going to be a 4-volume set on nanomedicine, and writing a book on replicators, and I'm also writing a book on diamond mechanosynthesis. So I'm trying to make Eric's visions a practical reality. Since then, there have been a number of theoretical advances and experimental advances leading toward the working out of that technology in a practical sense. And the ultimate goal of that is to build nanofactories and ultimately medical nanorobots so that we can all have very long, extended lives.
So when people think of a factory, they think of a big building, but these nanofactories will sit on a tabletop, right?
That's correct. Sit on the desktop.
They're going to be placing and positioning molecules and molecular fragments and even atoms, but obviously not one at a time, trillions or more at a time. How is it going to scale up to be so massively parallel?
Now, these tools, you have one tool operating at a time, but on a particular reaction. But you have many independent production lines in the nanofactory. You might have millions or even billions of separate production lines. And in each production line, you have a tool which is doing an operation, a particular chemical reaction, building a particular part of a nanopart that you're building. So many of them are being processed in parallel.
So just like on a chip today, you have billions of components. These nanofactories, which will sit on a tabletop, will have billions of little processes going on.
Exactly, and they'll have billions of processes going on at each scale. There will be some going on at the nanometer scale, and then there will be parts which are composed of 10, 100, even 1,000 atoms, and they will be feedstock to the next process, which has larger assembler arms, and they will be grabbing them and feeding them to still larger assembler arms, all the way up to the macro scale. At the highest level of the factory, the robot arms inside will be picking up parts and assembling them into larger parts, and the larger parts will then become parts of the nanorobots.
Can we, as an intermediate step, harness biological systems like a bacteria or some other type of cell which has a lot of capability and add non-biological materials to it, motors, computers, to have a hybrid biological, non-biological system?
I believe that's possible. What there has been a lot of work on recently is biorobotics, which is re-engineering individual bacteria. And you treat the genes as cassettes, and you can switch new ones in and take the old ones out and basically make them do what you want them to do, secrete new materials and that sort of thing. They've been able to take bacteria and engineer enzyme networks inside of them that are keyed to other molecules which fluoresce. And when you look at them under a microscope, you can actually see the lights twinkling. So they can make computer components like adders and half adders and things like that to do simple logic. The problem with that is biological components are inherently slow, and they're not as reliable as using purely mechanical components. When we are able to build with Diamond, we'll be able to build rod logic computers and very, very rigid systems that will do exactly what we want with a minimum amount of error.
So you mentioned red blood cells. A more complicated type of cell in the bloodstream is a white blood cell. What's the feasibility of creating basically robotic immune system cells, like T cells, and that would augment the immune system?
Yes, we could create artificial white blood cells. I've designed one on paper. It's called the microbivore. It would have more atoms than the respirocyte, about 100 billion atoms, a little bit more than 100 billion atoms in the microvivore. And it would be put into the bloodstream, probably about several billion of them, and they would go through the bloodstream and they would look for bacteria that they'd been programmed to detect. And like flypaper on their surface, the bacteria would stick to the surface. And then the bacteria would be transported into the mouth of the device, and inside the device, the bacteria would be digested. And then the remains would be harmless sugars and amino acids that could be put out into the bloodstream with no problem. And this entire process of digesting the bacteria would only take about half a minute. Now, a natural white cell takes about 100 times that long to completely digest a bacteria. So again, we have a situation where the medical nanorobot is 100 to 1,000 times faster or more effective in some way than a natural biological system.
And presumably you could program these or even download software to combat a whole variety of different pathogens, perhaps ones that our natural immune system was not evolved to deal with.
That's right. The microvivores could be programmed to deal with any type of bacteria whose antigen signature was known. It could even be programmed to deal with ones that were created artificially for nefarious purposes, or ones which had evolved in some obscure part of the world that nobody had ever seen before. As long as you know what the bacterium looks like on its outer surface, you should be able to program a microvivore to detect it and dispose of it.
What about viruses and cancer cells?
A version of the microvivore which had more mobility than the one that travels through the bloodstream would be able to go through the tissues and look for tumors. It would recognize the tumors the same way that it would recognize bacteria by the cellular antigen structure. And it could digest the tumors right on the spot. So essentially, a microvivore class nanorobot would be able to dispose of cancer quite easily.
And how about atherosclerotic plaque?
Nanorobots could also be used to combat arteriosclerosis. I would use a nanorobot called a vasculocyte, which is a small device that has lots of little legs on it, and you inject it into the bloodstream. It collects in the capillaries and forms up into traveling rings that then walk back up the vascular tree until they reach the site of the arteriosclerotic lesion. They then form up into a bandage and perform repairs. Another nanorobot called a chromalocyte would be the first true cell repair machine. Chromalocyte is also a very small nanorobot. It would be put into the body. It would travel through the tissues into your cell. Inside the cell, it would travel to the nucleus. It would there change out the chromosomes that are in your nucleus and replace them with newly manufactured ones that had been corrected, with all the defects in them corrected the way you want. It would then remove itself from the body, and the old genome would then be disposed of. So this is a key technology because it'll allow you essentially to roll back the clock.
One idea that I wrote about was to actually replace the nucleus itself with a little nanorobot that would basically act like DNA and actually include the ribosomes and be able to produce amino acid sequences that would then be folded into proteins and so on. What's the feasibility of something like that?
It might be possible to create a nanorobot which would entirely replace the functions of the nucleus. I think it would be technically possible. Whether it would be advisable, I'm not sure, because as a general principle, I would prefer to put nanorobots into the body, have them do their task, and then remove them. If you leave nanorobots inside the body for a long period of time, you get a number of other issues, biocompatibility issues, reliability issues. One of the nice things about biology is it is good at self-repair. A nanorobot, unless you give it the ability to self-repair, will not be able to do that, and eventually will break down.
My vision is we can begin to actually replace biological systems with engineered systems.
Yes, I have actually, with Chris Phoenix, designed a nanorobot system called the Vasculoid. And what it is, it's a replacement for the entire human vascular system. What it does, it's essentially a coating of nanomachinery over the entire vascular surface within your body. And materials are transported via a ciliary transport system with the materials like oxygen and carbon dioxide and nutrients and things like that transported in little containers. And this would essentially replace 9% of the volume of your body with nanomachinery. At some point, we start getting into the questions of what does it mean to be human? What is human? If you have 9% of your body replaced by machines, are you still a human or are you something else?
So you mentioned the possibility of nanorobots augmenting our natural immune system, but what about our immune system getting in the way? Would it react negatively to the intrusion of billions of these nanorobots in our bloodstream?
If we just put nanorobots made of diamond into the bloodstream, the biological system will react. It will react by depositing proteins on the surface. It will react by attempting to phagocytose them, which means a white cell will try to eat them and cart them off to a lymph node or somewhere else in the body, and we don't want that. So nanorobots will also have to have various biocompatibility systems, and these will make them invisible to the immune system and will also make them unable to be captured by white cells.
You mentioned nanorobots going into the brain and actually interacting with our biological neurons where they could monitor or influence the activity that goes on in the brain. And these will be computerized, so that introduces a concern about software problems like software viruses or software that would monitor what's going on in your brain or actually influence it. So how do we deal with that if we actually have software on nanorobots in the brain influencing what we do?
I think we're going to need, to avoid software glitches, we're going to need very strong laws prohibiting that sort of thing. We're going to need very good software engineering to prevent that sort of thing. We're going to have a lot of experience dealing with that beforehand because we're already building bionic equipment that people are using, artificial arms and things like that, which have chips in them. And that sort of abuse is already possible, and I'm sure there will be cases in the future where that happens long before we get to nanorobots. I expect that by the time nanorobots are deployed, which will be sometime perhaps in the 2020s or the 2030s, we will have a whole set of laws in place, regulations. There will be things you can and cannot do, and that's how we will deal with that.
Now, of course, the quintessential concern with nanotechnology has to do with self-replication. And of course, we know self-replication is a big problem in biology. And most disease has to do with self-replication. Bacteria, viruses, our own cells, in the case of cancer, prions. Self-replication causes disease. Nanorobots are inherently much stronger than biological systems, being built of diamondoids. So if they self-replicate, that disease, quote unquote, could be even a tougher problem than biological disease. So first of all, what's the feasibility of self-replication in the nanotechnology world?
I think it's possible to build self-replicating nanorobots. Whether that is the way we'll actually build them or whether we will use nanofactories to build them is up for discussion. It's probably safer to use nanofactories to build nanorobots. Is certainly possible for them to be able to replicate. As a general principle, you do not want to put self-replicating nanorobots inside the human body. I suppose not everybody agrees with me on that, but that is the way I think that we can best guarantee safety. If the nanorobots are able to replicate inside the human body, that means they are using some component of the human body as food, and we don't want them to be doing that. We want them to be going in and performing a therapeutic task and then coming back out again. Even in the case where you have an augmentation scenario where you're permanently installing nanorobots inside your body, you would still, even if you had them able to repair, you wouldn't want them to be able to reproduce. For the very reason that you described, they could get out of control, somebody could hack into them, and there just is no need for that capability.
So if there's, let's say nanofactories can take an information file and create an entity, and if one of those entities that could be created, or one type of entity, is a self-replicating structure of some kind, then that would be a very dangerous file to create. How do we prevent a terrorist or someone who's bent on destruction from creating such a self-replicating system, given that responsible practitioners will follow the ethical guidelines, but irresponsible ones won't?
Forestalling abuse of nanorobots in terms of building replicators, that has to be dealt with on many levels. One level, of course, is simply putting controls in the factory itself. And there are many ways to do that. And certainly the digital rights management technique is, some people don't like it, but it would certainly go some distance in that. Another way would be you would simply download the software from a central source, and that central source is very tightly controlled. So you could also use materials inside the nanofactory which were difficult to get, like we call them vitamin parts, and then restrict the supply of vitamin parts. Inevitably, in the future, there will be some acts of abuse, there will be some terrorist acts, because that's what humans do, unfortunately. So what we're going to be needing in this era of nanofactories is something equivalent to the fire department. And we have fire departments, they range all the way from a small fire extinguisher in your kitchen when a grease fire comes out of your pan, to a couple of engines that respond to a house that's burning on your street, all the way up to massive forest fires where thousands of people are brought in and huge amounts of equipment are brought in from government stockpiles. And I think we'll have a similar response scenario with nanorobots. Hopefully the incidents will be very few, but we will have an emergency regime which is set up to deal with that type of event. And according to how severe it is, the appropriate response will be made. Along with that, we will need a surveillance system of some type to detect the activities of unwanted replicating nanorobots. And we can do that. We could have satellite surveillance looking for heat signatures, because nanorobots generate heat when they work. And there's a number of other things that we've looked at that could be done to detect the threat and then respond to it quickly.
Now, the most daunting scenario in terms of the so-called gray goo attack would be a two-stage attack, a stealth attack, where the first stage, the biomass is sort of seeded, let's say at 1 per 10 to the 15th power. So it doesn't create a heat signature that you could detect by a satellite, because they're very few in number, but they're all over the place. And then when they start self-replicating in place, it would only take some 90 replications or some limited number of replications to then destroy the biomass. And you don't have this moving front of destruction that you could detect. So what's the feasibility of that, and how do we deal with that spectrum?
So when you contemplate possibilities like that, you need to have more than just monitoring of heat signatures. What you need to have, and this is one of the other things I was mentioning that I alluded to earlier, was that you need to have a method of sampling the environment on a regular basis. So we will send out devices which will constantly be sampling the dirt, the air, the trees, in some cases even living things, and examining what nanorobots are there, characterizing them and reporting them back to some central monitoring agency, so that we will have a good picture as to which nanorobots are where and what they are doing and who is in control of them and who their manufacturer is and who is legally responsible for them. And this sounds like a massive amount of data, but when you consider that we're going to be able to build a computer that will have the computing power of the human brain, that will have the volume of a bacterium, we really are going to have that type of computing power available to us in the 2020s and 2030s, which is when we would be thinking about starting to deploy this type of a system. The average person should care about nanotechnology because it is the most important technology that will be developed in the 21st century. In fact, you could almost call the 21st century the century of nanotechnology, just as you might have called the 20th century perhaps the century of electricity or automobiles or something like that. It is basically a game-changing technology. It's going to change everyone's lives in almost every way that you can imagine. As to when it will appear, it's going to be another decade or two before the really powerful applications of nanotechnology appear. So people can quite easily avoid thinking about it probably for another 10 or 20 years. But after that, they will have to think about it, and they will want to think about it because it will be so helpful to them. I have a message for my fellow baby boomers. Aging is a disease. It's a curable disease. Nanomedicine is the cure for that disease. We have the resources and the brain power to develop nanomedicine. All we lack is the will to act.
Some people talk about death giving meaning to life. Medical nanorobots really have the potential to extend human life more or less indefinitely, because it's very hard to imagine too many things that could terminate human life that we wouldn't be able to address with this type of technology. So what's your view about the role of death, and do we need death?
I have no patience for people who say that death gives meaning to life. I believe that life gives meaning to life. And I believe that our intellectual pursuits, our relationships with people, those things are what give the most meaning to life. And you can only experience those through life. Death is something that is an end. It's an end to life. It's an end to progress. It's an end to thoughts. It's something to be cured, not lived with.
I've written how there's an exponential growth of information technology, and of course we have Moore's law and even exponential growth before Moore's law in increasing the amount of computation. And ultimately we'll get to the point where we saturate the ability of matter and energy to support computation. So some people refer to this sort of ultimately saturated matter and energy as computronium. And ultimately we'll turn as much of the available resources that we want to without disturbing the biomass and the ecosphere into computronium here on Earth and in this vicinity in the solar system. And then we would have to move on out into the rest of the universe if we want to continue to expand computation. And since computation is going to be supporting intelligent processes, the expansion of intelligence would require that. So could you comment on how you see this developing, this expansion of intelligent processes into the rest of the universe?
If you do a projection of the total energy output that humanity is using and the current growth rate, which is about 3%, it looks like at about the year 3000 we would reach the total amount of energy that the sun is putting out. So at that point we will reach a new type of energy crisis. We will basically be limited by the amount of sunlight that we can receive, even if we put a collection shell all the way around the sun. If we don't want to go to that extreme, if we want to keep our sun in its natural condition, then we can content ourselves with a million-fold less computation limited to the solar system. Beyond that, there's an entire universe to go out and explore. And there are numerous ethical issues involved as to whether suns belong to those who find them or those who live there, or there's just many ethical issues. So it's not clear that we can just go around the galaxy willy-nilly, turning off suns and grabbing the hydrogen and using it to compute with. I think I would feel more comfortable if I knew that the computations were being used for some very useful purpose, such as, for instance, computing how to avoid the ultimate heat death of the universe. That seems like a fine objective to be computing. I think that the confluence of artificial intelligence and nanotechnology inevitably leads to something that we would all recognize as the singularity. I think it might be 2 or 3 decades from now, and this is based on my experience working with nanotechnology and seeing the rate of progress that we're achieving there. I am assuming that the rate of increase of progress in artificial intelligence is progressing at the same rate, and the two of them coming together will almost inevitably produce some type of singularity.